Hi Year 12. We're nearing the end of this chapter 7. We've got 2 sections to go, and today we're looking at rates and integration, and that will relate to 7E in our textbook. So what's happening in this section is we're going to most of the time be given a rate, for example, dV dt, which would be the change in our volume with respect to time, or something similar to what we had in our last exercise, like our bacteria growth, where we had a dB dt, the rate of growth of our bacteria given to time. And we then may need to go back and find, in this case, our volume, or the previous question, our bacteria, in which case we're going to need to integrate. It's going to come down to the language of the question again, because when we integrate, we're going to go and add plus C as a constant. And generally within that question that we're given, we're going to get enough information, and I'll show you in a minute in this question, to figure out what C is in this case. Occasionally, we'll not be given a rate at all, and we might be given a graph, in which case we'll be looking at the important features of the graph to figure out what we might be trying to work out. But in this case, I'm going to look at the example below and let's work through that together. The example says, the volume flow rate, so here's our note here, we're looking at a rate of water in a pond is given by dV dt. So the rate of flow of volume with respect to time is equal to 5 plus 6t squared, and we're in litres per hour. If there is initially no water in the pond, find the volume of water after 10 hours. So there's a lot of information that we've been given there. We know what our dV dt is. We know that initially we know that is time is equal to 0. At time is equal to 0, there is no volume in the pond. There's no water in there. And we want to find the volume of water after 10 hours. So what's our volume when T is equal to 10? So we've only been given that rate to start with. We want to find V's. We don't want to find our rate, so we need to integrate. So to find our volume, we're going to go backwards and we're going to integrate our dV dt with respect to T is what's going to happen. So let's find our volume. Let's go and integrate 5 plus 6t squared with respect to time, because time is our variable. Our volume is going to be 5t plus, we've got a 6, add 1 to that power, divide by that power, plus c. I'm going to neaten that up, and we're going to end up with 5t plus 2t cubed plus c. Now initially, at time equals 0, volume is equal to 0. So we can pop that into this equation here. So we're going to have 0 is equal to 5 times 0 plus 2 times 0 cubed plus c. So all I've done is popped a 0 where my v is, pop 0 is where time is, and I've got that my constant in that case is going to be 0. So 0 is equal to c. So I know that my volume is 5t plus 2t cubed plus 0. Find the volume of the water after 10 hours. So at t equals 10, v equals, that's what we're going to find out. So v equals 5 times 10 plus 2 times 10 cubed. v is equal to 50 plus 2,000, which is 2,500. What's our units? We were litres per hour, so 2,500 litres. So after 10 hours, our volume is 2,500 litres. Sorry, a little mistake there, not 2,500, 2,050 litres. Okay. That's the end of that section. I think I might show you another question that's a little bit more difficult that is not in your notes, however. So you can either stop the video here or move over into the OneNote into 7E and have a look at some of the examples in there, of which this is the first one. A tank contains 40,000 litres of water. When the draining valve is opened, so we'll think of it as a water tank, that's in your backyard, the volume in litres of water in the tank decreases at this rate shown. So the volume with respect to time is given by this value here, where T is the time in seconds. So we're not in hours, we're in seconds after opening the valve. Once the water stops flowing, the valve shuts off. So we need to think what's happening here. Okay, so initially at time is 0, we have 40,000 litres in our tank of volume. That's what we have initially. We then release the plug at the bottom of the tank and the water starts flowing out. And this is the rate that the water flows out in seconds. But we can shut the valve by just putting the plug back in or moving the lever and it stops flowing again. We don't know when that's going to happen. So that's basically the scenario that I'm thinking of. If you need to draw yourself a little tank and think of what's happening there, there might be a little plug or a little stopper at the bottom that you move that lever around and the water comes out. Part A says, when does the water stop flowing? This is a common sense question. I've opened the lever of the water tank. When does the water stop flowing? It hasn't talked about shutting it off. It stops flowing when the valve shuts off, but if I haven't shut the valve off, when does the water stop flowing? Well, we can't guess at this answer, and it's possibly going to be when the tank is empty, because that would make sense. Or maybe there's a little bit of water left in the bottom that can't get out the valve, but we need a value to assign to that. So when does the water stop flowing? When is our flow rate, our volume with respect to time, equal to 0? That's what that's telling me. This is my rate of flow that it's asking. When my rate of water isn't moving anymore, or my dVdt is 0, my water has stopped flowing. So I need to work out when minus 1500 plus 30t is equal to 0. So note that again, we're looking at the language on these questions a lot. So what have we got? Let's divide by 10. 3t is 150. What's t? T is going to be 50 seconds. So that's fairly simple. Our water stops flowing after 50 seconds. So if you visualize what's actually happening, that's a very large tank. That water is flowing very fast. So if it takes us less than a minute to empty that out. So it's probably got a massive spout, kind of like a fire engine would have. That's that size spout with the tank. Let's have a look at B. Integrate to find the volume of water in the tank at time t. So we've got dVdt. If we integrate dVdt, we will get V. And we want to sketch the graph of the volume as a function of time. So remember that in our calculus topics, we're still looking at functions. All of our formulas that we look at, we can still graph. So let's integrate this to start with. So to get our volume, we're going to integrate minus 1500 plus 30t, and we're going to integrate that with respect to t because that's our variable. So what we're going to end up with is minus 1500t plus, add 1 to the index, divide that 30 by the 2, and I'm going to end up with 15t squared plus c. Now, do you remember though, right at the start, we looked at the water tank and we said that initially at time equals 0, our volume was 40,000 litres. So I'm going to use that information to work out what my constant C is when I've integrated. So I've got that 40,000 litres is equal to minus 1500 times 0 plus 15 times 0 squared plus C. These parts here are going to go to 0, so I'm going to get that my C is equal to 40,000. So I now know that my volume function is minus 1500t plus 15t squared plus 40,000. I'm going to write that in a slightly different format, and I'm going to put the 15t squared at the start minus 1500t plus 40,000, because I can see there that that is a quadratic equation. Okay, and it's asking us to draw that. So what I might do because I don't like non-monic equations, I'm going to factorize out that 15. And what am I going to end up in there? I'm going to end up with, oh, that's a minus 100t plus 40,000 doesn't divide nicely into 15, but it does give me a little fraction that's a little bit neater. I end up with a very messy irrational number, so I'm going to leave it like that for now. And what we need to do for the second part of that question is it says, and sketch the graph of volume as a function of time. Okay, so it wants us to sketch this graph here. So if you're looking at the language of that and you're not sure what that means, sketching the graph of volume as a function of time. If we were to sketch this graph here, V and T, we've got two axes. The V is where our Y normally would be. The T is where our X normally would be. So it's just going to be a quadratic equation, but we need to understand that this is a real life example. Okay, so we need to put in the factors that are affecting that graph in real life. And our factors were that at time equals 0, our function had a volume of 40,000 litres. That's important, okay, because we don't have negative time. We don't want values higher than 40,000. So that's going to be our capped value for our volume. But we also found out at the start that it said, when does the water stop flowing? It stops flowing at 50 seconds. So that's where we're interested in looking at as well, is the 50 on the time. Now, a lot of you are going to assume that at time equals 50, the volume is 0, but that is not the case. Now, I don't know if you have tanks at home. If you do, I want you to go outside and have a look at your tank. If you live on anything over a couple of acres of land, you're probably going to have a very large tank, and you'll have a massive valve at the bottom. And what you will find that hole that the water's coming out of is going to be at a level that's not at the ground level, that's going to be a little bit above. So there's probably still going to be some water left at the bottom that can't get out the hole. Now, we need to figure that out with our function here, and I want to have a look at, although I know my volume starts up here, what is my volume at time is equal to 50? So let's work that out. At time is 50. My volume is, I'm just going to use that first equation, not the factorized one. So it's going to be 15 times 50 squared minus 1500 times 50 plus 40,000. Which, popping that in your calculator, we get a volume of 2,500 litres. So there's a little bit of water left at the bottom of that tank. So at 50, we've still got a volume of 2,500. So our graph, which is a parabola, is moving down in that pattern. Okay, and there's a picture of a tank that I've just popped out of Google, and that's what we're looking at. There's the large attachment at the bottom, and you're going to have some water below that, if that helps you visualize what's happened. Okay, so we're just about there. How much water has flowed out of the tank and how much remains? Well, we've pretty much answered that already. So we know that there's 2,500 litres remaining in that tank. We started off with 40,000 litres. There's still 2,500 litres in there. So what have we got? 37,500 litres has flowed out.